before I start with today's lecture, as Hiroshi kindly pointed out, I don't know how to divide by 2. So a correction from last lecture. From lecture 1, the top highest, so the top or the bottom conformal weight for the non-trivial, the non-vacuum module for SL2 hat is 1/4. So the representations of V1 SL2, they come, there's 2 of them. One is the vertex algebra itself, and the highest weight for this guy has conformal weight 0. And there's one module whose conformal weight, the top conformal weight, is 1/4. This is the lattice vertex algebra, where the generator has norm 2. So if you take half the generator, that has square norm 1/2, and then you need to divide by 2, which I didn't. So the basis for the chiral homology would be the vacuum vector plus 4 times, well, minus 4 times the conformal vector and 4 times the conformal vector. So thank you, Hiroshi. All right, so there's another mistake. There was another mistake, which is a subtle mistake, and I'll correct it along the way today. So nothing has changed. Nothing will change in the computations we did last time, but I need to be careful with in the construction of the complex. It's a very subtle thing that we'll talk about in a second. All right, so before starting again with today's lecture, so first of all, are there any questions from the previous one? Was there something that wasn't clear in the first lecture? Because that lecture was supposed to be the clear one. So starting from today, things are not going to be so easy. Thank you very much. Okay, so instead of starting with lecture 2, I'll continue with the things that I should have covered in lecture 1. One of them is the issue of the connection. So as I promised, our chiral homology should come with a connection on the moduli space of curves. I do not intend to give you the connection in general for arbitrary genus, but in the case of elliptic curves, this was a very explicit complex, so let's do that. Okay? So our elliptic curve, well, first of all, let's notice something. Our elliptic curve, remember, it was C divided by Z2, which is given explicitly by this parameter tau in the upper half plane. We will choose this isomorphism eventually. We will need this isomorphism. Not for now. So tau is in the upper half plane. And remember how our complex went? Our complex was we take functions on our curve minus our little mark point. The little mark point here corresponded to 0 in C or 1 in C star. So we allow poles along that point. We take a vector in V. We take a vector in a module, M. And we map to M by taking the residue map. So this was F, A, B, oh, I guess M. And we mapped it to the residue at T of F of T, A applied to M. Now, at no point I've used tau here. This clearly only depends on the curve X. So whatever I get is modular invariant. So this moduli space of elliptic curve, so if I replace tau by some action by a Möbius transformation of tau, I get the same curve, I get the same spaces, I get the same differential. So whatever I write, of course, is going to be modular invariant if I write it in terms of tau. Okay, so far, so good. Remember that we got to decide that we could pick a basis for this space by trading derivatives with V. Being that basis, function 1, the constant function, and the versus p function, because I could quotient this whole space by the relation. So I could, this differential here factors through this space that is a quotient of functions. By the relation where I can take a derivative with respect to t on the function or apply t on the first factor v. T on m doesn't make any sense because I'm not even requiring m to have a t. So this factors like this. And then I could choose a basis here to be the constant function or the versus p function. But how about the connection? So in order to write a connection, I would want to keep I want to consider all taus at the same time. So instead of fixing one tau and looking at functions like this, now I want to consider all taus at the same time. So what I'll, yes? No, so in the quotient? No, so in the statement here again was integration by parts. The residue of the derivative is 0, therefore this whole thing is in the kernel of the differential, so I can just take it out. And the homology in this degree is not going to change. So now it's something that I'm doing ad hoc. Later, when I continue this complex, this is going to become important because I took out something from here. And the homology, of course, is going to be different if I consider this object or this object. And this is the right one. And I'll give you an intuition why that has to be the right one. But before doing that, let's consider all taus at the same time. So how do I do this? Well, I'm going to replace this m by functions from the upper half plane to m, holomorphic functions into this m. Okay? So, and I'm going to replace this space by a different one, considering all taus at the same time. So let me define gamma 1 to be meromorphic functions on C times H. So these are going to be functions of t and tau. They have some properties. So I'll require that this f of t plus m plus n tau is equal to f of t. Oh, tau. So that they give me functions. Once I fix tau, these functions are functions on this elliptic curve x, on the corresponding elliptic curve x for that given tau. But I'm also going to allow them to have poles. So f is allowed to have poles at t in the lattice, where m and n are integers. Okay. So these are functions. Once I fix tau, this set of functions is the same thing as the set of holomorphic functions on the curve minus the given point. Okay, so I'm going to consider those functions, and I'm going to take the same differential. So I'm going to take gamma 1, tensor v, tensor m, and I'm going to map it. Well, this thing, whatever I do, is going to depend on tau. So I'm going to map it to, I could say, gamma 0 tensor m, where gamma 0 is just this with one less coordinate. So this is just holomorphic functions in tau. In tau. Or I could say holomorphic functions from the upper half plane into m, but the map is the same. You give me f of t and tau. You give me a vector in v, a vector in the module, and you take the residue at t. And you keep the tau dependence. Okay? So now, in this space, I'm going to write again, I'm going to write a connection that is going to be completely ad hoc at this time. All right, so which functions am I considering? Well, of course, the same functions that I already had are well defined. They satisfy this. So I could have taken, this is a valid function satisfying these properties. The constant function is a valid function satisfying this property. And we know that essentially derivatives of this versus p function multiplied by any holomorphic function in tau are the only things that are valid here. So it's holomorphic functions in tau multiplied by this, or any derivative of this. These are all functions of that form. But there's one that I want to consider, which is not in that set, which is the Weierstrass zeta function. So this guy here is going to be defined in such a way that the derivative of this with respect to t is minus the Weierstrass p function. So that's a formal integral. This is a function that is meromorphic on all of C times the upper half plane. It has poles of order 1 and residue 1 at each one of these lattice points. And of course, it cannot be bi-invariant, because if it was biperiodic, then I would have a function with one single pole and no non-trivial residue on the curve minus 1 point. Well, on 1 point on the elliptic curve. So this is not biperiodic. What it satisfies is that zeta of t plus 1 of tau is zeta of t tau. But zeta of t plus tau is zeta of t minus, perhaps I'm getting this sign wrong, but the constant that you pick up is a constant that depends on tau, and that constant, here's a zeta of t tau, and that constant is G2 that I defined in the previous lecture. Okay, so this function is not, yeah. If I normalize that the first, yeah, no, I'm sure I pick up a G2 here, and we've used this. So it depends on whether or not you include G2 on P as well, and whether or not I include G2 on zeta. We've chosen different normalizations in our own papers. But this is a constant. This is a constant, and this constant depends on tau. And let me tell you what the only thing we will need of this function is that this guy looks like, well, let me give you I told you what the Taylor expansion of this p function at t is equal to 0 was. And remember, that p, I wrote it as 1 over t squared plus the sum of 2k plus 1. Here k is bigger or equal than 1. Here is g2k plus 2. Yeah, so that's what Jethro is pointing out here. And here I got a t to the 2k. And this zeta of t tau is going to be 1 over t minus the sum, k bigger or equal than 1, of g 2k plus 2, t to the 2k plus 1. So that the derivative of this guy gives me that number, that thing there. All right. So that's what I will need of this zeta function. This zeta function is not allowed in this set. It's not allowed in this factor here. However, this formula is well defined. And I can just take this formula using that explicitly that zeta function. So I'm going to just define ad hoc that connection. So this connection is going to be a differential equation that is going to come from defining that nabla tau, or this is the action of d by d tau on the moduli space, is going to be given, well, I need to tell you, of m. Well, this is going to give him, by definition, is going to be the differential of, well, that zeta function, tensor, the conformal vector, and here I will need, and this is the first time that we actually need the full conformal vector, tensor m. So explicitly what this is oh, so this is, let's d by tau. So this is the action of the vector field d by d tau. It acts on this function gamma 0 by just differentiating it with respect to tau. This factor wasn't there when I fixed tau, and it acts on the other guy by adding this. And this is explicit. This has the following form. So I need to take the residue of the zeta function, the conformal vector, applied to M. And remember, the conformal vector t is the sum of ln t to the minus 2 minus n. So this residue is explicit, is the minus 2 product, which is L minus 2 of M. So that's the first residue, plus the tail of that thing, which is some G 2k plus 1. Then, so k here is bigger or equal than 1. And here I'm going to have L2k plus 1 applied to M. Okay. So now I've given you a vector bundle on C, or on the upper half plane. That depends on, so the fibers over tau are the chiral homology of degree 0 when I fix this tau. And I can look at sections of that bundle co-flat with respect to that connection. So modulo that differential equation. Or dualizing this, and this is what people often do, instead of looking at this homology, they look at the dual of that homology. And that leads to the notion that was originally written down, in this case of genus 1 by Zhu, which is the notion of conformal blocks, which is the dual of this complex. So I'm going to take M to be V here, and I'm going to take the dual complex. And I'm going to take the homology of that complex in degree 0. So the cohomology of that complex in degree 0 is called the conformal blocks. Conformal blocks of V in genus 1. And what is explicitly, well, M is V here, so I'm going to be looking at linear functionals in V. In general, I would be looking at linear functionals in M, but, well, I'm going to take the dual. So this is linear functionals in V that kill the image of the differential. So such that phi of d of something is equal to 0, and that d of something is very explicit. We only need to kill the constant function, and that leads, when I take residues, to expressions of this form. So this should be 0. And I need to kill the Weierstrass P function. And remember, this was A minus 2B plus a sum of 2k plus 1, G 2k plus 2, A 2k, correct, B, k bigger or equal than 1. So I need to satisfy these two identities. But now with this space of linear functionals satisfying these two identities has, gives me something well-defined over the whole upper half plane when I allow for functions, holomorphic functions on tau, when I let tau vary. And then I'm going to require, I can look for flat sections. So if I let tau vary, I can ask, when do I have flat sections? And flat sections became an explicit differential equation. And the differential equation is that d by d tau. Did I write tau? Yeah, tau is correct. D by d tau of phi of A is equal to phi of the residue, well, what I wrote right there, which is L minus 2 of A plus the sum of G 2k plus 1, L 2k plus 1, So those are flat sections of the bundle over the upper half plane of conformal blocks on the elliptic curve whose fiber, well, that's given by that tau, parameter tau. All right. And we've proven that that space is finite dimensional, provided that was what we did last class, provided that this space is finite dimensional. Implies that that space is finite dimensional. All right. Okay, so that was all I want to say about connections. Perhaps I should say something more. So how about changing the point? How about allowing this m to live on different points? And let's put several m's at the same time because we can kill that quickly. So to allow several points, let's do this on a different board. And this is where this connection is going to become interesting. So let's do this for different points. So now instead of having functions on t and tau, and t allowing to have a pole at 0, I'm going to just take functions on several variables, and I'm going to allow them to have poles at specific points that I'm going to change. So I'm going to consider this space gamma, which is going to be meromorphic functions. Morphic functions of, well, t0, that's going to be my previous t, then t1 up to tn. These are where I'm going to be putting my modules. My modules are going to be lying over t1 up to tn. And t0 was the original function that I had here. And then tau, that is going to live in H. These guys are in C. And they should be biperiodic on each ti, and allowing singularities at t0 is equal to ti plus m plus n tau. So I allow a pole there. Allow a pole there. And also I want my points to be different. So I'm going to allow singularities at ti minus tj in m plus n tau. Although this is irrelevant, I'm going to pick them, t1 up to tn, fix them to be just n points. And the differential is what you think it is. The differential is simply you take those functions, you take your vector from V, you take the collection of your modules, mi, and you map to the collection of your modules, mi, and you give me this function f of t, 0. Then this, you have t1 up to tn. You have your vector a. You have the elements of your mi's. And you're going to map this to each one of the expansions of this function as a function of t0 along each one of the points ti's. So I'm going to take my f, and it's going to have such an expansion for every I. This is sum over, okay? So this is a function that will depend on t1 up to tn, no longer on t0. And it's going to have a t0 minus ti to the k. And this is a Laurent series that starts at some integer number. So you're going to send the image of the differential is the sum over all points i's and over all k's of this guy, which is constant once I fix the points t1 up to tn. So this is fik, t1 up to tn. Again, these are constants once I fix these endpoints where I put them. And then I'm going to take m1 tensor. And in the ith component, I'm going to take ak acting on mi. So this now gave me a vector space, which is the zeroth homology of that guy, of that complex, over every point in C to the n times the upper half plane. So I've just constructed a vector bundle over C to the n times the upper half plane. This is where I put the points T1 up to Tn. Of course, this is going to be invariant by the Jacobi group. This guy is where I put my tau. And I just construct the fiber of this is the homology of this complex there. And this comes with a connection, and this connection is no longer flat. So now I already told you what d by d tau is. Now I need to tell you what is the connection when I change these points T1 up to Tn. And that connection is given by, how does this guy act? Well, it acts as you expect. You will take d by dti on the function f, and you would act by t on mi. And this will require something on the module. So this will be d by dti plus t on the factor I. So what is this guy? Well, now I need something in my modules. So now my modules are conformal. Or my vertex algebra is conformal. So this means L minus 1 acting in the ith factor. And what's interesting is that these guys will not commute in general. Yeah. Well, so you can take it either way. So if you fix tau, this is as it is. If you let it change, then you need to tensor this by holomorphic functions in tau. Because the target will depend on tau. In this, Blackboard is fixed. And in this one, it's not if I want to allow this. Otherwise, just don't think about this and just let them, the TIs change. You get to pick. So this defines a bundle over the moduli space of elliptic curves with endpoints. And you can just fix the curve and just change the points. Or you can just let everything vary. OK. So let's go to hierarchical homology, which is what I wanted to do today. So again, we need some intuition from Lie algebra homology, which I'm going to write slightly different. Remember how it was for Lie algebra homology? The differential was something like this. So let me change this slightly now. Let me write this as G tensor k plus 1 to G tensor k. And I'm going to take a quotient here, and I'm going to take a quotient here. And the differential, I'm going to tell you first on the ambient space. This had two sums. You can do this now faster. A0. I think I was doing it in general with coefficients in a module. So let's do this with coefficients in a module. Let's do this with coefficients in a module. So here I take k. I is missing. And then we act. AI acts on M. And the other summand is, perhaps I got this plus 1 wrong, but I'm going to take AI bracket AJ tensor A0, AK, tensor M, and here I and J are missing. So this quotient is there's a natural action of the symmetric group on k plus 1 elements here and k elements here, and you quotient by it, which is the alternating action of the symmetric group. So the quotient means take invariance with respect to k plus 1 or sk here, where the action is when you exchange two guys for a transposition, you put a minus sign. But the important thing to check today is that, well, you write that differential at the level of the tensor products, and you check that d squares to 0 is implied by the Jacobi identity. And it's enough to do this. Well, that's the Jacobi identity in the case M is equal to G, or the fact that M is a representation in the general case. And it's enough to check this. The computation in general is the same, but it's enough to check this from K is equal to 2 to K is equal to 1 to K is equal to 0. So it's enough to check this from this tensor M to this tensor M to M. And if you grab A tensor B tensor M, that differential there should send it to A tensor. Well, I think with the signs I've chosen, I might get this wrong, but I think my signs there are of the form A acting on M minus A tensor B acting on M. And I've put a plus 1 here, so this is going to be plus A bracket B tensor with M. And now the differential there is just the action. So this goes to B A M minus A B M plus the bracket of A with B M. So that seems right. And the fact that this is 0 is the fact that M is a representation. If I had taken the adjoint representation, this would be the Jacobi axiom. So I want to check the same for vertex algebras. So we want to get the same intuition. We want to write a complex, and whatever we write, we want to get the Jacobi identity, which is the axiom for vertex algebra. Yes?
So you want this differential to vanish without taking...
No. So, no. I want to take the symmetric group. I want to take this quotient. Yeah. I will need skew symmetry. I will need skew symmetry here. I wrote this in a way that appears that I'm not needing anything, that I just need the Leibniz rule, but I need both identities. That's correct. So, and this is something that Jethro is pointing correctly that we are going to actually use. So if I write it this way, and I say, well, this differential actually is compatible with the symmetric group action, well, I can put this guy anywhere. And we can do this by putting this bracket instead of at the first spot. We can put it in the jth spot and have only I missing there. And we are going to do that, actually, precisely. So Jethro is ahead a few words, but I could replace this by something that looks like A0 tensor. I is going to be missing. And then take AI with AJ in the jth position. And nothing changes. And, well, some sign might change. I might need to take out this j plus 1 or just probably a j. I won't care about those details. And that's actually the differential we're going to take now. So remember what was the complex that we needed? So we had this black box. There was this vector bundle with a connection that we had on the curve that I didn't tell you what it was because I told you that this guy was a limit. This was a union of guys like this. So this came filtered, and we had the associated graded was very explicit to be the tangent bundle of the curve. This doesn't fit there. V minus n minus 1 into V less or equal than n into omega x to the minus n tensor with our vector space Vn in the vertex algebra. And this is what we used because it gave rise to the same kind of homology. But let's just stick to this for a second. And what we need is we're going to need the following. I'm going to take dk is going to be inside of xk. It's going to be a divisor, and this divisor is going to be given by the diagonal guys, xi minus xj, where 1 is less or equal than I, less than j, less or equal than k. Or I'm going to allow singularities at my mark point, which is the, I was using xi's for the mark points. So this is probably a bad idea. So let's, well, let's mark some points, which now I'm going to mark them to be y1 up to yn, which are going to be the mark points where I put the modules m1 up to mn. So I have k copies of the curve, and I have m modules that live at very precise mark points on the curve. So I'm going to take a divisor next to the k, which are the diagonal divisors. This is when the vertex algebra operations is going to be singular, and then I'm going to allow the vertex action on the modules. So I'm going to allow that the ith point is that guy. So okay, so what I will take is section. So this is going to be the analog of g to the k plus 1 tensor m, or probably g to the k tensor m. I'm going to take sections on all of xk, and I'm going to allow singularities there. And we've already decided that we needed singularities in these spaces to see the full OP. So I'm going to take out this, and I'm going to take sections of this bundle taken k times. So I'm not telling you what this is, but I wanted to correct something. So this is k copies of this bundle. And then I'm going to take the tensor product of all my modules. These are n of them. So I didn't tell you what this bundle is, but I did tell you what is going to replace this whole thing, and it's going to compute the same homology. And that thing is take the sum over n1 up to nk of sections on, again, xk minus that divisor of omega x minus n1 box omega x minus nk. And here I'm going to tensor with v copies. So this is going to be vn1, vnk, and then I'm going to take the tensor of my modules. So you choose a bunch of vectors in your vertex algebras of conformal weight n1 up to nk, and you choose a bunch of vector fields on your curve. Well, vector fields to the n1 up to vector fields of the nk to the nk, but you allow extra singularities. So if you only choose vector fields that way, you're not allowing any singularity. So you allow to multiply locally by a function that has singularities at this decay. So that's going to be the entrance of my complex, and I'm going to have to take some quotient of this thing by some symmetric group action, just like I did for Lie algebras. So here's the subtlety that I missed in the previous time. Already for degree 0, I missed this, and it's the following. This thing here comes with a flat connection. This is a left D module. When I'm taking global sections on an affine curve, this is not really going to change much because I'm trivializing anyways the omega. But what I need to do, and you see it immediately from here, to have a natural antisymmetric action of the symmetric group, I'm going to tensor this guy by omega x. And this amounts to converting this left D module into a right D module. So you can take all these factors of omega x out, and this is the same as gamma of x to the k minus dk of this same guy that I had before, tensor, with the canonical bundle on x to the k. So that this guy became a right Z module. This is locally in coordinates, which is how we're working. This doesn't change anything. The differential has exactly the same form. And here, the picture is that we're just going to add 1 to each one of these factors. But it's the same thing. The differential is exactly the same that I wrote before. Locally, you pick a trivialization, so you pick coordinates on your curve, and the differential is going to be exactly what I wrote before, which I'm going to rewrite again now. Okay? And I'm still not telling you what this bundle is, but I'm telling you what this complex is, and the differential is going to be explicit. So the differential is what? You pick coordinates, local coordinates. So this is a complex that is computed locally. And, well, so a section there is going to look like a function of T1 up to Tk. Well, let's choose T0 up to Tk. So that I take k plus 1 now instead of k. I'm going to take a differential. And it's a function because I've already trivialized this thing. So I should write this d by dt 0 to the minus n plus 1, n1 plus 1, d by dt times d by dt k to the minus nk plus 1, which I'm not going to write. So I'm going to have this. I'm going to have a0. I'm going to have a k. And I'm going to have the collection of guys in my module, which for simplicity, I'm going to take only one module. I could take a tensor product of mi of n of them. But this is the form of this guy. And I should be careful because the way I'm writing here, this guy should be of conformal weight n0. This guy should be of conformal weight nk. And I'm going to be in the summand n1 up to nk, which I'm not caring about any of this. So what is the differential of this thing? So again, two sums. And to take those sums, I'm going to make these expansions. For each one of these i's from 1 to n, in this case I only have 1, I'm going to have an expansion of my function f where the ti coincides with that where the module lives. So let me, yeah, probably I want to fix those. So let me use coordinates, different kind of coordinates here. Let's use x0 up to xk, and let's put these guys. mi from I1 to n. And I'm going to have f I k I don't know if I'm going to be able to write it here. So what I want to say is I'm going to grab this function that depends, okay, it's about 9. I'm going to expand this in each one of the i's and each one of the j's for the module when that coordinate xi is equal to yj. Okay. So I'm going to take I, j. I was using k, so now it's going to have to be p. And this is going to be a function that will no longer depend on xi. So I is missing. And now I'm going to multiply by xi minus yj to the k, to the p. And this is a Laurent series around that point. Of course, this depends on all the coordinates that I've chosen, but the final homology will not. Then I also will need expansions. Let's say this is module expansions, and this is vertex algebra expansions. I, j, p. Again, same thing, x0 up to xk, and xi is going to be missing. And this is going to be xi minus xj to the p. So the only difference here is that this function was allowed to have singularities also when the two on the diagonals. And now I'm going to copy those two summands there. So the two sums are, one sum goes from j is equal to 1 up to n. This is the action on the modules. And, well, let's do this correctly. So I have I that goes from 0 up to k. Then I have n j that goes from 1 up to n. And then I have p that is bigger than the maximum pole of that expansion. I'm going to take f I j p. I'm going to leave the vectors a0 up to ak as they were. I is missing here, and I'm going to act by ai by taking the pth product acting on n. Oops. Oh, shoot. I'm going to take m1, and in the jth factor, I'm going to act by ai by taking the pth product of nj. So that's the action of the vertex algebra on all of these guys. And then I need to have one for the multiplication of the vertex algebra. So again, this is I, well, now is 0, less or equal than I, less than j, less or equal than k. And I'm going to put I, j, so this was the module expansion, this is the vertex algebra expansion. P, again. Now, instead of using this, I'm going to use what Jethro pointed out. So I'm going to take a0, tensor, and in the j, the I is going to be missing. And in the jth position, I'm going to take ai, the pth product, aj, ak, and I'm going to leave all the guys invariant. The modules are not going to change. So now there's a bunch of things that I need to tell you. First of all, signs, and I have no clue about them, so I think it's here -1 to the I. And here, I think it was -1 to the I. Perhaps it's -1 to the I plus 1. We're going to check it when we check Jacobi in a second. So the j does not appear because of my choice of putting this guy here. Okay, but the tricky part here is that the function I started with is a function of k plus 1 coordinates, and I want to land in a space where I have xk minus 1, and, well, xk and sections here. So sections of this thing depend on k coordinates, not k plus 1. And yes, indeed, these coefficients depend on k minus 1 coordinates. Oh, sorry, k plus 1 minus 1 coordinates. But the problem is that they depend on different ones. So if I take the fi expansion, I took out I, and then if I take the fi plus 1, I took out I plus 1 out of this. So when I write this, I'm explicitly telling you how did I identify the coordinates of this function. So I am evaluating all of these functions on the same set of coordinates, and those set of coordinates are t1 up to tk, just as they appear. Namely, if I take a function that depends, so when I did that expansion, I would have seen something of the form 2, 3, p, and this would depend on t0, t1, t2 would be missing, but t3 would be there, and I would see a t2 minus t3 to the p, and I'm reading this here evaluated at t1, t2, t3. Oh, sorry. t1 and t2. Okay. Oh, I'm being silly. t1, t2, t3. Okay, so I evaluate all of these functions at this set of coordinates. Okay, theorem, this thing is a well-defined differential. And I need to tell you in which quotient. So, first of all, we're going to quotient by the action of the symmetric group on k plus 1 elements on these guys. How does the symmetric group on k plus 1 element act? Well, if you give me some f of t0, tk, a0, ak, and a bunch of modules, the modules are completely relevant for this action, then, and a sigma here, you send it to -1 to the sigma, the sign of that guy, f of t of sigma inverse of 0, t of sigma inverse of k, a sigma inverse of 0, a sigma inverse of k. So that's the obvious action. And this differential is compatible with that action. Namely, if you just act first and then you map, it's the same thing as mapping and then taking the action of the symmetric group. That is false per se. So I need to quotient by something else so that that statement that I just made is actually true. And what is the something else that I'm quotienting by? This is something that you should guess immediately. What I'm saying is that whatever this homology is, it should be a cohomology that does not depend on these points where I'm taking this multiplication. So this is something that should depend on the curve x and the points where I put my modules, but certainly not in these variables x0 up to xk. So if I look at this and I look at this quotient given by this differential, I still see the variables t1 up to tk in this differential. I need to get rid of them. How do I get rid of them? I'm going to quotient by d by dt I plus t in the ith factor, which is exactly what I did in the case m is equal 1. So we already knew that we needed to quotient by this. Okay? So in the case to compute chiral homology in degree 0, this came for free that we could divide by this, but now in higher degree we have to divide by this. And we need to divide by this to make this statement true. So what happens is, if you do this at this level, you take the differential, you permute two of these guys, or you permute them first and then take a differential. The difference by skew symmetry differs by an element which is in the span of these guys. So you need to kill this. Okay, so that's it. That gives us a complex, which is not quite right yet, and I'm going to tell you why in a second. But this is good enough already to compute chiral homology in degree 1, so that's what I'll do. And I want to talk about filtrations, and I want to do, I should have probably said something about degree 0. So remember last time, we took the Hodge filtration in degree 0. We looked at functions on x minus a point, OX. We were computing homologies with coefficients in the vacuum module, and we took a filtration, an increase in filtration on V, and we took an increase in filtration on these functions. And this increase in filtration on these functions was 0 inside of C times 1, inside of everything else. And that was good enough to prove that this bounds chiral homology in degree 0. So question is does this work for arbitrary genus? The only thing we needed is that we had a section P. There was a section of O2 that was locally of the form 1 over t squared plus something that is regular. Given the properties of the filtration for the vertex algebra, that's all we needed. The problem is that, so one would guess that this should work also for arbitrary genus, but the problem is on arbitrary genus, the way we're defining this is by sections of x minus a point of omega x 1 minus n tensor Vn tensor V. And then you need to sum over n like this. And this guy is of negative degree, so you're not going to find sections of this form. So the Riemann-Roch theorem is going to guarantee that you may, well, it's not going to guarantee, you may not have sections of this form. Already for genus 2, you may not have sections of this form. So I do not know how to prove along the same trivial lines that chiral homology is finite dimensional if you have this condition. So if you look at Damellini, Gibney, and Tarasca, they proved this. Well, this was known before. It's known that for rational C2 cofinite vertex algebra, so when RV is finite dimensional, these spaces are the chiral homology is finite dimensional, and I do not know how to adapt the proof, the trivial proof that we gave last time, to that situation. It would be nice to know that. But I want to adapt the trivial one that we gave works for elliptic curve. And that also works for Carrier homology in degree 1. So what I'm saying now might not work for general curves, but certainly does for elliptic curves, and that's where I want to focus. And I want to check that this is a differential. Okay? So let's check that this is a differential. And for this, I'm going to stick to elliptic curves, although the proof is obviously the proof that d squares to 0 is local. So I'm going to give you something that is already trivializing omega x. Therefore, I can talk about functions. But the proof works for an arbitrary curve. Okay? Since it's local, I can use coordinates. Okay, so I'm going to look at our situation in the simplest possible example, which is x squared minus d2. Sections of this, I'm going to do this. I'm going to stick to elliptic curves. But of course, you can replace by vector fields here without a problem. We're going to have v 3 times, or actually, we're going to have, let's do this in general for a module, v 2 times and a module mapping to sections of one curve minus the one marked point OX, tensor v, tensor m, and then mapping finally to m. I've already told you what this differential is. This differential is function, vector, and vector in the module. Take the function, take the guy, apply it to the module, and take the residue. So that one is easy. Let's look at this one again. So here is a function that depends on two coordinates, t1 and t2. And it has poles at t1 is equal to t2, or t1 is equal to 0, or t2 is equal to 0. That's this divisor d2. And I'm going to take the three expansions, which are this function here is going to be equal to f1 of t2, t1 to the k, the sum over all k's, or is going to be equal to the sum over k of f2 of t1, t2 to the k, or is going to be equal to the sum, again, over k, of f1 to k, oh, this is f2k, this is f1k, and this is of t2, t1 minus t2 to the k. So I'm taking the three expansions near t1 is equal to 0, t2 is equal to 0, or t1 is equal to t2 that are the possible poles for that function. And I want to read down now this differential here. This differential is very explicit. It says that the differential of the function f, tensor A, tensor B, tensor M, is equal to, I may have gotten the signs wrong there, but okay, so I'm going to write them with the signs that I've chosen there, and then we'll fix them. So the first thing I need to do is I need to apply A0 to my module M, and that comes with a sign plus, which is different than what we chose in our paper, it seems. So I'm going to take the sum of f1k. This depends on one coordinate, which I'm going to call it t. That depends on only one coordinate. Tensor b, tensor a, k, m. Then I have minus the sum of f2k. This depends on only one coordinate, so that coordinate is again t. Tensor a, tensor b, k, m. And the last summand here is I need to apply the multiplication of a on b and put them in the position of b. And this guy comes with a plus sign, and it is f1, 2. Well, let's put it there below. Is the sum of f1, 2k. This depends on one coordinate, again, t. The three of them are evaluated in this set of coordinates, same set of coordinates. And now I have tensor A, K, B, tensor M. I left M alone. Okay, so that's what the differential is. It's very explicit. And now let's take the differential of that again. Okay? So I'm going to take the differential of that again. Now I have a function of one coordinate, so I need to take B, apply it to this vector, and take the residue at T. Okay? So this guy let's evaluate d of that guy. D of that sum of f1k t tensor b tensor a k m. What is that guy? Well, this is the sum over k of the residue at t of f1k t b of t a k m. But this in itself was already a residue. This a k m was the residue of t to the k, or t2 to the k, applied to, of a of t2 applied to m. So I can write this as a double residue, where I take the residue at t1 of the residue at t2, and I can put my function f of t1, t2 that I started with, b of t1, a of t2, m. And this is the first summand. The second summand is minus. It's of the same form. It's just that now I take the residue of t2 second, the residue of t1 first, the same function f of t1, t2. Now I have a of t1, b of t2, m. Oh. Yeah, so let me change these names. Actually, I would want to take the other way around and shift these signs. So I want to always evaluate A on T1 and then B on T2 and then take this of T1, T2. Yeah. Where did I exchange these things? So I want to change the names of this. Well, let me put it like this. Let me just keep it like it was. I may have confused T1 and T2 at some point. And then the last one is, again, a residue. But this one is a different residue. This is the residue of T1 minus T2, and then the residue at T, just check, at T2. And this is A of T1 minus T2 applied to B. Take that field and apply, I need still to multiply by f of T1, T2. Take that field and apply it to M. Take that guy of T2 and apply it to M. So this is, the three of them are double integrals. And I may have screwed up at some point here because what I want to get is not this sum. I want to get here T1 and here T2, and here still f of T1, T2. So find where I screwed up these two guys. Here I should have gotten B of T2, A of T1, applied to M, without changing f of T1, T2. Because the fact that these three sums add up to 0, this is the Jacobi identity, and this was the definition of vertex algebra according to Alberto de Sol. So this is the definition of a non-unital vertex algebra. So that's the Borges identity. The fact that the sum of these three things is equal to 0. Except that I just confused these two, which perhaps we should do, but I don't want to do this on the board. So the Borges identity says that the residue of A of T1 applied to M, then B of T2 applied to that, times any function. Oh, I see. I've taken the residues in a different order. Correct. So if I change this to T1, then a residue of T2, then this becomes like this way. Correct. I can take B of T2, B of T1, A of T1, apply to M. And this is, well, if M is V, this is a Borges identity. If M is an arbitrary module, this is the definition of having a module. The fact that this sum of these three things is equal to 0. Okay. So we have a differential. And now I want to compute H1. again, the same thing. I should check that these claims that I made before are correct, namely that I can divide by d by dti and then t acting on the ith position. But since this differential, you see, this guy here was a residue. This is the residue of t2 of f of t1, t2, and then a applied to m. And since this is a residue, the same argument as before says that I can just trade the derivative with respect to t1 of f of t1, t2 by tensor A, tensor B, tensor M, or I can just take the original f times t of A, tensor B, tensor M, and this goes to 0. Again, by integration by parts. So this goes down to that quotient by d by dt and the translation operation acting on the ith factor. And once you do this, the last one that remains to check is what happens if I exchange A and B, and if I exchange T1 and T2, and check that this thing is the same. You're going to need skew symmetry on the vertex algebra, and it's going to be true that these two differentials are the same, modulo an expansion in these guys. So the explicit computation is carried out in our paper. It's not so pleasant, but it's not so bad either. It's just exchanging these two factors, apply to skew symmetry. All right, so what I wanted to do today, and I'll try to get as far as I can, is these conditions to have finite dimensional chiral homology, at least in degree 1. So again, this is now genus 1 and degree 1. Or degree 0 we already did, and degree 1 I want to start today. So these are two different set of limits that we're going to take. This is the classical limit. We're taking a filtration on V, and we're going to take the associated gradient. In the last lecture, we're going to take, tomorrow we're going to take a different limit, which is going to be the nodal curve limit. So these two different limits I want to relate. So today I want to see arc spaces, or most probably tomorrow. And certainly tomorrow I want to see the Jou algebra appear. And that's all I want to cover. Okay, so what I will do is, again, on the space of functions, now I need to describe functions on x squared minus this guy. And before I gave you a filtration, I'm going to give you the same filtration that is going to be the Hodge filtration. So this, let me call this space gamma, or gamma 2, and this is going to be the Hodge filtration. And you're going to define this GP the following way. Let me just say it instead of spending time writing it. It's going to be, you're going to take functions that locally have poles at most p components on this divisor D2. This divisor D2 looks like the diagonal and the two guys that are 0. So you want to have functions with no poles, then functions with poles at most one of these components locally, linear combination of those, then functions that have poles at two of them locally, and then a combination of those, and there's nothing with functions with 3 poles that is not coming from below. So explicitly, let me tell you what is a basis for this space, modulo derivatives, because we have that. We have the constant functions. Well, first of all, we have 0, which is going to be g minus 3. We have the constant functions that is a basis for g minus 2 of gamma 2. The next guys are going to be functions that have only one pole at one of these components, and those are going to be g minus 1 of gamma 2. And these, well, are going to contain the constant functions, but I also will allow functions like these ones. The Weierstrass function on, these are functions on two coordinates, x and y. This guy has a pole only at x is equal to y. You could have, for example, p of x. You could have p of y. But here, there's something new. On x squared, there's something new. The zeta function actually contributes. So let me define this function. This function is the zeta function of x minus y minus zeta of x plus zeta of y. Zeta was not biperiodic, but this combination is, because if I add to x tau, then this guy spits up minus g2, and this guy spits up a plus g2. So this thing is actually bi-invariant. And this is a new function that appears here. And these are not linearly independent modulo derivatives, because if you take the derivative of the zeta function, you're going to get a combination of p functions. So if you want modulo derivatives, you only need these two. There. So this means modulo derivatives. But you allow the derivative of those. Those are still going to be in g minus 1. Just as for the case of the Hodge filtration of the elliptic curve, we had the p function in g minus 1. And the derivative of the p function in g minus 1, etc. So t is going to, the derivative with respect to x and the derivative with respect to y preserves this filtration. The thing that I'm not going to allow in g minus 1 is this function. For example, p of x times p of y. This guy, even locally, has poles along two of these components. So that guy is not going to be allowed in g minus 1. And the same for p of x minus y, zeta of xy, which is also not going to be allowed because that guy has poles 2. But actually, I'm going to put every function in this g minus 2. I'm just saying that these two guys are in g minus 2, but g minus 2 of gamma 2 is going to be the whole gamma 2 of x squared minus d2 ox. And the claim I'm making is that these 5 functions that I wrote generate the whole space by derivatives. So I have the constant function, these two guys, and then these two guys, and they generate, yes? Oh, yes, thank you. I'm increasing. This is G0. Thank you. So if you take these 5 functions and you take derivatives of those, you generate all of this space of functions here, just as we did for the case of one copy of the curve. And this number 5 is the dimension of H2, the RAM, of this affine variety. H2, the RAM, is C5. So that's a basis for that thing. And this is the top, the RAM cohomology of that. This is the top Betti number of this variety. H3 is already 0. In general, the top homology of x to the n divided minus this divisor, dn, that you can guess what it is, well, you're going to express it in terms of functions. This is non-trivial to do, actually. Well, anyways, so that's my filtration. I'm going to take the associated gradient. So claim. Well, let's see if I can give you intuition for why this claim. The complex that I just wrote is filtered. So I'm going to have GP of gamma 2 tensor V 3 times now to GP of gamma 1 tensor V 2 times, and this goes to GP of V. So this is functions on x squared, functions on x1. This is the part that we've already proved. The fact that this was filtered, I already proved. I need to tell you why this guy is filtered. Okay? And again, since I can trade derivative of functions by t acting accordingly on the corresponding factor of v, it's enough to prove this for a collection of functions modulo derivatives. And I just told you what is that collection of functions modulo derivatives. So how does this complex look like? So the first observation is that if that complex is filtered, then I'm going to pass to the associated graded. And then when I pass to the associated graded, I only need the associated graded of V, which is a Poisson vertex algebra. So knowing something about Poisson vertex algebras would bound the chiral homology of vertex algebras. And this is general. But OK, let's prove why do I expect this guy to be filtered? Well, this is what we have here. Just have 3 copies of V. And then we're going to have this piece where we have 2 copies of V. And then we're going to have V. So now functions. In here, I needed 2 functions. I had this guy. Oops. I had this guy that was in G0. And the constant function that was in G minus 1. And all the derivatives of these guys were also in G0. So this generates G0. Here, I'm going to have 1 in degree minus 2. I'm going to have 2 functions here, P and the zeta function. So this is the zeta function of x, y. So linear combination of these 2. And then here, I'm going to have P times P or P times zetas. Combination of those. Now, on this guy, I only have the constant function 1. The claim is that the derivatives go in this direction or horizontally. And it all boils down to the same thing. It was a property of how do we compute this differential. How do we compute the differential? We take a residue. When we take a residue on a function with k variables, the resulting function has 1 pole less. We took a residue at ti is equal to tj. The resulting function has a variable less, has 1 pole less. So we never increase the number of poles. On the other hand, when we take a residue, we also apply a vertex operator. So what we're doing is we're taking a residue at ti is equal to tj of a function of several variables, t1, tk, and then we're also applying that field ai of ti minus tj to another guy. And the vertex operation, if I take a negative power of ti minus tj, preserves the filtration. That was the property of the filtration. But if I take a positive power here, it goes deeper in the filtration. Remember, that was the basic property of the filtration in V, that A and B is in GP plus Q if N is negative, or GP plus Q minus 1 if N is non-negative, where A is in GP and B is in GQ. So the point of this is that when I take a residue, there's 2 things that can happen. My function was singular and I lost that pole, and I only care about the singular part of my function, and I preserve the filtration. Losing a pole seems like it increases the filtration in the Hodge filtration for functions, but it doesn't because I am shifting by -1. So this 1 was the function with no pole, this is in -2, and now it's in -1. So that preserves the filtration. The other thing that can happen is, well, my function was regular. And in this case, well, you see, so this I missed. You can have this. So if my function is regular, then I'm going to go deeper in the filtration, so I don't see anything. Okay? So I only see singular parts of my functions, and I can only remove a pole or maintain my poles. Okay? But I can never make a new pole. So I cannot go this direction that would remove 2 poles, for example. I can only remove 1 pole at a time. And I cannot make poles. So the differentials go like this. And once I realize that I cannot make poles, namely I cannot go from something like here to here, and I cannot remove 2 poles, so I cannot go down in this diagram, then I see immediately some subcomplexes. So this is going to be a subcomplex. There's no differentials coming out of that top row. So let's analyze that subcomplex today. Okay? So I told you this differential is graded, And we've analyzed this differential the previous time. What is that differential? I take P, A, B, and I map it to the residue of the P Weierstrass function A of t applied to B. But the only thing that contributes here is A minus 2B, because the rest is regular and it's deeper in the filtration. Once I pass to the associated graded, this is the only part of the P Weierstrass function that matters that is of the form 1 over t squared. It's as simple as that. So in the associated graded, that guy looks like this. It looks like just the associated graded of V. It looks like A tensor A, and the map is to A, and this map takes A tensor B to A minus 2B. So the homology of that top complex in degree 0, we already know what it is. Let me call this complex, let's put a name. I'm going to have to stop in now. So I'm going to call this complex K. The homology of the complex K in degree 0 is RV. I have the Poisson algebra, and I'm dividing by ATB. So I see immediately this homology. How about this homology? The image of this, and here this. Well, I have these two functions, and there's something quite interesting. This function zeta has poles of order 1 at each one of the 3 components of the divisor. So if you compute explicitly the differential of this guy, the differential of P zeta, so again, this is P of x minus y, zeta of xy, A tensor B tensor C, and you only look at the singular part because the regular part gets killed because it goes deeper in the filtration, then what you find is that this is the Weierstrass P function tensor A, B, tensor C minus A tensor BC minus B tensor AC. Everything else is deeper in the filtration. So we see that this A tensor A modulo the image of this differential, which is the Hochschild differential. So this is the Hochschild differential for A, as simply as a commutative algebra, or as an associative algebra, which happens to be commutative. So when I quotient by the image of this differential, I get omega 1 of A. But I still have the other function. I still have this PP. I still have like 5 minutes. So modulo the differential. So modulo the image of the differential of the Weierstrass P function times the zeta function times A tensor B tensor C, we find omega 1 of A in degree 1 in the homology of K. But we still have the differential of this P function times P function. So this is, you can take it to be P of x. It doesn't matter which combination you take. All of them lead to cohomologous elements. You can take P of x times P of y, tensor A, tensor B, tensor C, and you compute the homology of the differential of this explicitly by taking residues, and you only care about the singular part of this function, which is 1 over x squared, 1 over y squared. So you immediately see from here, you get something of the form A tensor T of B times C minus B tensor T of A times C. So this, when I identified in A tensor A squared with the subspace, the quotient, which is omega 1 of A, I see the following. That the homology we've proven the following proposition. The homology H dot of the complex K in degrees 0 and 1 agrees with the homology of the following complex: omega 2 of A, omega 1 of A 0. This goes forever. But since I'm only claiming this homology for degree 0 and 1, I could stop there. But let's just say from omega k of A to omega k minus 1 of A, you always have a complex. This is called the Kojoule complex. Whenever you have an algebra A with a derivation, in this case is T is a derivation, you get on the Derived space of that algebra, you get a complex which is contraction with the derivation. So explicitly what this is, here an element of this form goes to A TB, and here an element of the form A dB dC goes to A TB dC minus that's correct. So minus A TC dB. So that's the contraction of T with each one of these guys. And the kernel of this modulo the image of this is this Kojoule homology. And by the differential that I wrote, the homology in degree 1 coincides with this Kojoule homology. So let me finish with the following statement. I don't want to remove this because this is kind of we're computing this, which is subcomplex, and then tomorrow I'm going to compute the cone. But here's something that I would like to do in detail tomorrow, but let me just state it because it's how arc spaces appear. So let A be a graded differential algebra generated in degree 0 as a differential algebra. So A is A0. Well, A is the sum of A0 of AN, n bigger or equal than 0. And in A0, in this case, is RV. So if you have a graded differential algebra with a derivation of degree 1, then the homology of the Kojoule complex, let me call it HK1. So the homology in degree 1 of the Kojoule complex of that algebra is 0 if and only if your algebra A is the arc space of A0. So there's a couple of, so I don't have time to write anything, so I'm going to prove this in the next case. But this is how this condition of classical freeness appears in chiral homology. We took a subcomplex that's going to bound the homology of the whole complex. In degree 1, we found explicitly this Kojoule homology in degree 1. And this guy vanishes, which is something you want to prove. If the chiral homology vanishes, you're going to need this vanishing, or at least it's going to be useful to have this vanishing, if and only if your vertex algebra is classically free. However, this is very unnatural. I am using that A is a graded algebra with T of degree 1, but A appeared with a filtration that makes T of degree 0. So A appeared in our picture as the associated graded with respect to the least increasing filtration, where T is of degree 0. So I'm using here a theorem of Tomoyuki that says that A is isomorphic as a Poisson vertex algebra with the one coming from the leaf filtration, which is decreasing, where T is of degree plus 1. And that is an isomorphism of Poisson vertex algebras, which is not an isomorphism of graded Poisson vertex algebras, of course. That's why I'm taking A0 to be RV. With respect to the usual leaf filtration decreasing, this is true. And with respect to that filtration, this T is of degree 1. So it's interesting that we found A with an increase in filtration, then when we need to prove that theorem for the different grading of A. Both gradings are playing a role here. So I'll try to give more details in that, and I'm going to finish this computation tomorrow, computing this part of the complex. All right. And we should see the Poisson homology again. Sorry that I took a minute. All right. Okay, so I'll see you guys tomorrow.